Okay, and here's Cody Cat with the 6.4 learning target. I can identify linear and nonlinear functions. So we have this little note here that tells us that linear functions have a constant rate of change. A constant rate of change. So I'm actually going to zoom down here to these pictures. Yeah, I'm looking for a constant rate of change, which looks like some kind of straight line. Well, this is a curve. The rate of change it's changing over time. It starts by increasing very fast, and then it slows down, and then it starts increasing very fast again. It's not constant, so this is a non-linear. This is a perfectly straight line. It doesn't have to be flat. It could have been at an angle. The key is it's straight and perfectly straight. So this is linear. Linear is fancy talk for line. Okay. And then this last bit here, this does not count as a linear function because it's not one straight line, but it's split into two separate lines. So as one function, we call this still a non-linear function. All right. Okay, now the tables are a little trickier. I'm looking for a constant rate of change, which, by the way, this is AKA slope. I'm going to write that here too. How about we go AKA constant slope. If the slope changes, then it's nonlinear. So let's take a peek right here. Let's look what's going on. So on the x-axis, we're going over 3 each time. And on the y-axis, we're going down 8. And that happens each time, it looks like. So my slope then, we say m equals down 8 over 3. There's my slope. Slope is -8/3, and that stays constant the whole time. If I look over here on the x-axis, I'm going up 2 each time. So far, so good. And on the y-axis, we are going, well, from 2 to 11, looks like it's up 9. From 11 to 33, I'm going up 22. And then from 33 all the way up to 88, that's going up 55. So every time we go over 2 on the x-axis, we're going up by a different amount on the y-axis. So this is non-linear. That slope changes. And that's because 9 over 2 is not equal to 22 over 2, which is also not equal to 55 over 2. In fact, you could say that this is increasing at an increasing rate. But anyway, the key is this is non-linear, and this was linear. Linear. Okay. Cody Cat requests that you pause and try the next problem on your own before moving on. We're up 2. Up 2. Ooh, and then this is interesting. From 8 to 14, we went up 6. On the y-axis, we are up 3. From 4 to 7, we're up 3. From 7 to 16, we're up 9. Well, very interesting. You might think that this is nonlinear, but it turns out I could write this slope as up 3 over 2. 3 over 2, that's the slope between 2 points. 3 over 2. And then between these 2 points, I'm up 6 over, I'm up 9 over 6. So I could also say that slope is up 9 over 6. And either way, well, this fraction actually reduces to this fraction. Either way, the slope is equal to 1.5, or 3/2. So this is still a linear function because the rate is still the same. It's still a constant rate. Okay, and last but not least, we're looking down here. What about these equations? Well, to identify a linear function, it should be able to be written in y equals mx plus b form. Y equals mx plus b. So you should be able to tell me a slope and a y-intercept. If you can't, it's nonlinear. A few other things that you can use to spot nonlinear functions is, one, you can't have a variable in the denominator. That will guarantee that this is nonlinear. This one, the slope is 0. Slope would be 0, but the y-intercept is 4.7. That's a line. In this one, you have a slope, or an m, of pi, and you have a y-intercept of 0, so this is still linear, y equals mx plus b. And then this one here, I could rewrite this if I distribute here. This is the same thing as 4x minus 4. Slope of 4, y-intercept of -4. So a, b, and d are all linear, but c is nonlinear. Here's another way to spot nonlinear. If you see an exponent like this, we could pretend we have e, an equation that looks like y equals, I don't know, how about 2x to the 3rd power? If you have an exponent like so, then it would be nonlinear. Okay, thanks for playing that 6.4. Have fun.